Okay, shout out to Ella. Anybody want to say hi to Ella?
Stop being gross.
Ooh, wow. Who else are we missing? Is that it? Say hi to Ella.
Hi, Ella. We love you. Hi, Ella. Come back.
Ella, please stop dying.
Ella, we miss you. Okay, please, at the top, write this down. What is that symbol called? It is called the integral symbol. A to B of f of x. Do you remember what comes after f of x? Dx is equal to the limit as n goes to infinity of what? The sum, good, from I equals 1 to what? N of f of x sub I times delta x. And then we computed a couple things that we're going to write off to the side. Do you remember what delta x was equal to? That refers to the width of each rectangle. How is it that we compute the width of each rectangle? B minus a over n. We're going to use that today. And then we also have x sub I we said was equal to a plus delta x times I. Again, as you look at it, looks ridiculous, but we make sense of it. And we start always with this. Consider the area beneath the curve, f of x equals x cubed from 0 to 3. What will be the width of n rectangles?
From the integral scroll, is like A would be the first and then B is like the second, so you read it from bottom to top.
Yes. Yep. Good question. What will be the width of those rectangles? 3 over n. You take the width of the interval, which is 3, and you divide it by n. Any question there? We move on. For what x values do we evaluate the sum? X sub I is going to be equal to what is a? 0 plus what is delta x? What's your width? 3 over n times I. Or in other words, 3I over n. Those are the x values at which we evaluate the sum, or the heights. Any question? Good, then we're ready to move on to this piece. Express the definite integral as a limit of a Riemann sum. Integral, what to what? 0 to 3. What next? Which is x to the third dx. This is the calculus representation using the integral. We're going to show you how to do that next week in a different way. It's going to be really cool. Right now, what we do is we add up the area of an infinite number of rectangles. We always start out with the limit as n goes to infinity of the sum from I equals 1 to n. Now this is where we got to try to remember what we did yesterday. This is the piece that you want to try to think about. It's f of x sub I. So what do I do with this x sub I thing? Plug it in for the, I plug it in for the function. So it becomes 3I over n cubed. So I plug that in, and then what is this? Times 3 over n. So to summarize, we found the width, we found the spots where we evaluate the heights, and then we wrote it as an infinite limit of Riemann sums. Let's just multiply it out. I'll even use a little space here. the limit as n goes to infinity of the sum from I equals 1 to n of, let's see what this gets us. So I equals 1 means we start with the first rectangle, and then we go to the second, the third, and the fourth. We go all the way up to an infinite number. So that's the rectangle that we use. It's always 1 to n. But if we cube this, you get 27i cubed times 3, 81i cubed over n to the fourth. Do you notice how the I has a degree that is 1 less than the n? That will always be the case. If that's not showing up, then something is incorrect. Okay? All right. Now it says factor leaving an expression with only I. So what we want to do is we want to pull out everything that doesn't have an I in front of this. So we have the limit as n goes to infinity of, Maddie, I think you saw it. What goes in front of that summation? 81 over n to the fourth. Good. From I equals 1 to n. What's the thing that remains on the other side of the sigma? I cubed. Yesterday, we said we're going to take this and get rid of it. Look on your page and see if you can find with your friend what's the formula that you put in for that. See if you can find that. Look for it. Okay, is that what you put in? Did you find that n squared times n plus 1 squared over 4? Great. So really, if you think about it, just so that we can make sure we see all the parts, width, not a big deal, right? The spot where you evaluate the sum, not a big deal. Plugging it in, sometimes this is where people make this mistake, is they're trying to write this out. But once we write it out, all we got to do is just pick the right thing to plug in, which is right here. The rest of the way, we just have, a basic, almost like an algebra problem. We're just finding an infinite limit. It's no big deal. So I'll write it out. We get the limit as n goes to infinity of 81n squared times, and what is n plus 1 squared? N squared plus 2n plus 1 all over 4n to the fourth. If you want to, you could choose to get rid of the n squared and the n to the fourth right now if you want. Do you want to reduce that right now? It's if you would rather just multiply it out, you can, or you could start to cancel some things right now. So that's fine. So I'll write it as the limit as n goes to infinity of, we know that that's going to cancel with 2 of those. So what do you get in the top? 81n squared, 162n, plus 81. So I'm taking the 81 times each of those. All over 4n squared. Now, we learned this before. How is it that we evaluate an infinite limit? What do you factor out of the top? Yeah, limit as n goes to infinity. Factor out that n squared. And what are you left with? All over Yep. 4n squared, however you want to write it. What happens? N squareds are gone. As we let the limit go to infinity, what else happens? Those go to 0. And what are you left with? 81 over 4, which is 20.25, right? Take out your calculator. So I'm going to try to verify that my answer is correct. This is how you can check your answer. I want to be clear on the test. I do allow you to use your calculator. I check all of your work all the way through. So sometimes people just write down the answer from their calculator. I don't give you credit for that. Okay, you got to show your work all the way through, just like we're doing here. I type in x raised to the third power. I'm going to zoom standard. That's the cubic, and we want to see the area bounded from 0 to 3. What do I type in on my calculator? Calculate. Number 7. Lower limit is 0. Upper limit is 3. And it found that area 20.25.
I like that.
You like that?
I like that.
Oh, you like the calculator part. So, okay, so Hannah brings up a real... Okay, folks, please talk to the person next to you and decide what is different about example 6. Go ahead, talk. Okay, anybody out there, what's different? Yeah, there's actually 2 parts to this, right? And so we're going to see what happens when you have 2 different parts. And then tomorrow, the example we'll do, there'll be 3 parts, and we'll switch the starting point instead of 0. It'll be like 1 or 2 or something like that. And that will complete our work. So we're gonna we have some confidence now. We're gonna build by putting by having 2 pieces here. So let's start with the basic. What's the width of the n rectangles? 4 over n. Great. For what x values do we evaluate the sum? Remember that x sub I is equal to a, your starting point, and you're going to add delta x times I to it. Yeah, so people are seeing right here that a is what? 0. So if a is 0, then all you got to worry about is just taking your width, which is that thing, and just multiplying it by I, right? So that's all you have to do. If the starting point is different, let's say the starting point was 1, it would just be 1 plus. That's all that means. Just take the width and attach an I to it. So all of a sudden, that's become pretty easy, hasn't it? Holy cow, we're already at C. You try to write this out right now. Don't try to actually multiply something, but just see if you can write it out on your own. Take about 2 minutes, and then I'll write it, and you see if you get it correct. Okay, let's look up here. Did everybody get the definite integral written correct? We've got 0 to 4 of our function dx. Good. Equals the limit as n goes to infinity of the sum from I equals 1 to n. And now what we have to do is we have to plug this thing in here. So it's 2 times 4i over n. Okay, so I plug the 4i over n in there. Minus 1/2 times 4i over n squared And I'm going to end a parenthesis because it's all of this times your width. So a mistake that people make is they don't put the width times everything. Everybody okay with that? Okay, that's going to be a little bit more work than our previous one, isn't it? Yeah. But fortunately, we're really smart. Like, just think of how challenging this would be if we weren't smart. You know, that'll be tough. So we got that going for us. Limit as n goes to infinity, sum I equals 1 to n of, and I'll take it step by step so we don't make a mistake. This turns out to be what? Okay, so I've got 8i over n minus, yeah, this would be 16i squared, wouldn't it? But then multiply it by a half, so we got 8i squared over n squared. And all of that is times 4 over n. Yeah.
So, like, when you use the 4i over n, and then, like, get 8i squared, how do you keep y and x? Yeah.
So 4i squared is 16i squared, and n squared is n squared. But now I have to multiply it by a half. So I get a half I squared over n squared. Yes, no?
Yeah, okay, I gotcha. They're separate. Like,
We okay?
I know, yeah.
All right. Limit as n goes to infinity of the sum from I equals 1 to n. What should we do now? Distribute the 4 over n, and you get 32i over n squared. Notice how the I is 1 degree less than the n squared. See that? That's important. Minus 32 I squared over n cubed. Notice how the n is 1 degree greater than the I. That has to happen. Okay? Now, so your thought now is, well, what do we do? Like, we got two different things, right? No big deal. We just write two different sums. Limit is n goes to infinity. And what part do I pull out of here? Yep, so we got 32 over n squared times the sum from I equals 1 to n. And what remains? Just I. And then minus another sum. And so here we're going to factor out 32 over n cubed. Sum from I equals 1 to n of I squared. So we just turn it into two sums. So because it's subtraction and sum relates to subtraction, you just create it into two pieces. It's no big deal. Okay, see if you can figure out what do you plug in for these two. Find them. We're almost there. We just got to plug something in and do the algebra, and we're done. Okay, what do I put in for this guy right here? Just the first one. Good, so I got n times n plus 1 over 2. And what do you put in for the next one? Good. Does everybody see what we plug in? So, and every class is different, and so, but would you like to get rid of some of these n's right away? So I got n over n squared, right? So I could bring that down to just one n, and I could bring this down to n squared, or two of those n's. Okay with that? You want to do the 32 over 2? You guys want to do that? 32 over 2 is 16. I guess you do 32 over 6 if you want, which is 16 over 3. Equals. So let's write it out. We did a lot of work. You guys are almost there. What's in the top for this piece? 16n plus 16 over what's in the denominator now? Just n. Minus, I'm going to have to multiply this out, aren't I? So we get 2n times n will be 2n squared times 16 will be 32n squared. Good. And then we'll have 2n times 1 and n times 1, which will make 3n. And 3n times 16 is 48n. And then we have 1 times 1 is 1, times 16 will be. And then what goes in the bottom? 3n squared. So notice I didn't distribute the subtraction sign. I'm just going to do this and then subtract that from it. Okay. So we're almost there. Limit as n goes to infinity. What do we factor out of the top? And you're left with 16 plus 16 over n minus, what do you factor out of here? N squared, you'll have to 32 plus 48 over n, 16 over n squared over 3n squared. So what do you want to do? Okay, so Maddie sees here that this n and this n cancel, and that this goes to 0, leaving me with a grand total of 16. Minus n squareds cancel. Those go to 0. So I get 32 over 3. If you decided to make them into thirds, it would be 48 thirds minus 32 thirds, which is 16 thirds, or 5.3 repeating. And I can't resist, it's just so cool. We take out our calculator. What is our formula that we have? Is it 2x?
2x minus half x squared.
X squared. I press graph. I've got my graph. Looks like I'm going from 0 to 4 right there. So I press second calculate. I do number 7 from 0 to 4. And it makes all those little boxes. And I get exactly that. It's pretty cool, isn't it? Yeah. Yeah, it's sweet. It's sweet. And if I could just do one last small piece, and you guys can get going. Remember, the whole idea is we take the width of the rectangles times the sum of the heights. And so again, this is the calculus idea. What's happening to the width of the rectangles? It's moving towards. The number of rectangles is going towards infinity, but the width of each rectangle is going towards 0. And then since you have an infinite number of rectangles, the height's going towards infinity. And so we're wondering that big idea, like which one wins out? Turns out it's 5, 0 times infinity is 5.3 repeating there. And as we talked about before, 0 is like 1 over infinity times infinity, or in other words, what is infinity over infinity, which is what we kind of started this class talking about. So it's a pretty cool kind of big connection there. So you have time now. Looks like I posted the wrong answer key. I would really try to encourage you before the hour's out to try to get one problem knocked out. Feel confident with it so you can look at that and say, yay, we can do that. I think excellent problems to try right now would be problems 1 and 2. Three and 4. Yeah. I think 5, 6, 7, 8 you would want to do after we start tomorrow, okay? So those would be good places to start. I'll post that answer key. I'll come around and help you. Good job today, you guys. Bye, Ella.